Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today we are going to discuss our lesson 9, which is all about gas stoichiometry as well as a discussion on diffusion and effusion. So at the end of today's lesson, what I want everyone be able to do is first apply the principles of stoichiometry to determine the amounts in terms of volume, number of moles, and the number of mass or the mass of a compound, more specifically a gaseous compound, either it is a reactant or product. I hope you guys remember what stoichiometry is. Basically, is a relationship between reactants, products to products, or reactants and products, wherein we look for the relationship from the chemical equation that we have. And since gas can also participate in chemical reactions, we can apply the principles of stoichiometry in terms of looking for the volume, the number of moles, or mass in terms of a gaseous compound. And lastly is for us to be able to relate the rate of gas diffusion with molar mass. In here, we would actually learn another law which helps us describe or identify the behavior of gas, or in this case, we are looking for the relationship in terms of the rate of effusion. Later, we will learn what diffusion is and its relationship with the molar mass of gas. So let's begin with our discussion with gas stoichiometry. Previously, we learned stoichiometry in a way that we only have been using mass and moles of compounds, right? If we have a certain mass, or if you have a certain mole of a certain compound, we can find the related compound, either whether it is a reactant or product. We can find the possible mass and moles from that chemical equation. So this is basically what was happening. This is the skill set that we learn. For example, we have a certain amount of reactant and we want to find a certain amount of product in terms of grams. What we usually do is we take the given grams of a reactant and then we multiply it with its molar mass in order for us to change the grams of the reactant to the moles of reactant. Afterwards, we find the relationship between those given and what we are looking for. For example, in this situation, perhaps you were given a reactant and we're looking for a product, a certain amount of a product. So the mole ratio that we will have is between a ratio of that reactant and the product. And we usually get this from our equation, right? And then after finding that, we will end up with having the moles of our product or what we are looking for, and then we can just change that into grams. This skill set is basically a general use of what stoichiometry is, and it's not only a relationship between the reactants and the products, but it can also be from reactants to reactants. For example, if you want to find how much reactant will react with the other reactants that we have. So for example, if we have reactant A and reactant B, how much reactant B do we need in order for us to fully consume reactant A? We can still apply the same principle. We will take the given amount of reactant that we have and then change that into moles, and then from that moles of reactant we can find the mole ratio between the two reactants, and then we will end up having a moles of reactant or reactant B, and then we can just choose convert that moles into grams using the molar mass. That is the whole process of stoichiometry. But also there are some situations wherein gas is included in stoichiometry. The only difference is that for a gas we usually use a volume. So what we need to learn is for us to be able to convert gas from volume in terms of liters to moles. How are we going to do that? Well, we can do that by applying ideal gas law. So we are going to we're going to add on to our skill set on stoichiometry, but this time we are going to apply this in terms of gaseous reactions. So what happens is this top part right here is basically what we know. One thing that we want to add is how to convert moles of reactant or moles of a certain compound, either a reactant to a product, and change it into liters if we are dealing with gas. Because if we have gas, we usually use liters to define the units of gas. And in order for us to do that, we have to use our ideal gas law, which is the pressure multiplied by volume is equals to the number of moles, which is the N, or T. R is our universal gas constant R, and T is our temperature. So using this idea, we can actually find, for example, a certain volume of a gas, product, or reactant. So for example, if we are given a certain amount of reactant and we are looking how much volume we have of gas do we have as our, for example, we will have a gaseous product, how much volume of the gas do we have? So we usually have to begin from what we are given. For example, we are given a certain mass in terms of grams, and then we just have to use this same skill set that we have. You have to change that into moles of reactant, and then in this case what we are going to do is we have to change that moles of our reactant into the liters using our ideal gas law. And from there we can use the molar ratio to find our reactant to product ratio, or basically what we are given to what we are finding. Using the molar ratio from our chemical equation, we can find what we are looking for. So now what we are going to do is we're going to look at a sample problem. So this is a sample problem 9.1. Airbags are incorporated to ensure the safety of car passengers. One of the substances used in the mechanism of airbag inflation is sodium azide, or NaN3, which is triggered by the impact of the collisions of cars. The composition of sodium azide is shown in the following reactions, wherein we have 2 moles of sodium azide and it decomposes into 2 moles of sodium and 3 moles of dinitrogen, or N2. The one responsible for the inflation of airbags upon the composition of sodium azide is the formation of nitrogen gas. So this N2 right here is a type of gas. What is the volume of nitrogen gas produced at 85 degrees Celsius and 875 millimeters of mercury by the decomposition of 78 grams of sodium azide? So we're going to do is we're going to take this and we're going to solve this, but we will be moving to note in order for us to do that. Okay, so here's our sample problem. Okay, so let's begin this sample problem by first writing our given. Okay, so from our problem, we are given a certain amount of sodium azide, right? So we are given also a certain temperature and a certain pressure, because at the end of the day what we want to find is the volume of our nitrogen gas. So our gas is nitrogen and it is our product, right? So let's write our given. So in this chemical equation is subjected at a temperature of 85 degrees Celsius. Moreover, it is at a pressure of 875 millimeters of mercury. And then we are also given the mass of our sodium azide, or NaN3, which is equal to 78 grams. And another thing, like I've mentioned in just a previous discussion that we had now, in order for us to do this, we have wherein we are looking for the volume of, in this situation, our product, we have to apply ideal gas law. And in our ideal gas law, we are using a constant value R, which has a value of 0.0821 liters atmosphere over mole Kelvin. So what it's asking is basically the volume of N2. We are given a certain amount of reactant, which our reactant here is sodium azide, And what we are looking for is from the grams of our reactant to volume of a product. In order for us to do that, we have to apply not only stoichiometry but also ideal gas law. So our formula would have to include ideal gas law, which is PV is equals to nRT. So let's go ahead and solve this problem. So the first thing that we have to do is to make sure the units, our units are appropriate. So if there is something that we have to convert units or convert given units to appropriate units. Why do we have to do this? Well, because we are using a constant value of R that has a unit of liters atmospheres and mole Kelvin, which means our pressure should be in terms of atmosphere and our temperature should be in terms of Kelvin. Therefore, if we want to change our temperature into Kelvin, in order for us to do that, is we have to take the degrees in Celsius and just add 273.15 Kelvin. So our temperature would basically be 85 degrees Celsius plus 273.15, not Kelvin, and that will that will give us basically a temperature of 358.15 Kelvin. So now we have an appropriate unit for our temperature. Next, we have to convert our pressure from millimeters of mercury to atmosphere, because again our R is in terms of atmosphere. So we are going to have our given atmosphere of 875 millimeters of mercury, and we just have to convert this by multiplying this to a conversion factor. Our conversion factor is basically the relationship between millimeters of mercury and ATM, an equivalence value, and we know that in every 1 atmosphere is actually equal to 760 millimeters of mercury. So the millimeters of mercury gets cancelled, and what we are left is basically 875 times 1 divided by 760, or that is about 1.15 13 atmosphere. So this is just conversion. We've done this. I hope you guys still know how to do this. Okay. Next, after converting your units, what you want to do is basically find volume. That's our ultimate goal. Find the volume of N2. But before we can do that, we have to first find the moles of N2. And we will get the moles of N2 from the mass of NaN3. So this mass of NaN3 and moles of N2, we can do this in terms of stoichiometry. So this is where our stoichiometry is going to happen. So we have to find our mole ratio. What is the mole ratio? I hope you guys remember. We will get this from our balanced chemical equation. So another thing that you have to make sure is that you will have a balanced equation. Upon checking this, you will see that on your reactants, you would have 2 sodium, and you also have 2 sodium on your product. And here you would have 6 moles of nitrogen and also on your reactants, and also 6 moles of nitrogen on your product. So now you will just have to find the relationship between your N2 and your NaN3, which is your product and your reactant. Right? So the molar ratio is basically in every 2 moles of your reactant NaN3 is equivalent to 3 moles of, basically there is a production of 3 moles of N2. So your molar ratio is 2:3. And why is this useful? Well, because we have to find the moles of our N2 before we can find its volume. So in order for us to do that, moles of N2, we will begin by looking for our given, which in this case we are given a 75 grams of NaN3, and we have to convert this into our moles. This is just basic stoichiometry, right? So, if you look at your table of elements, you will be able to compute your molar mass for NaN3. And the molar mass of NaN3 is actually in every 1 mole of NaN3, you have about 65.02 grams of NaN3. So this is just the molar mass. Again, I hope you guys remember how to find that. So the grams of NaN3 gets cancelled. You are left with moles of NaN3. So now from moles of NaN3, you can change this into moles of N2. And you will get that from your mole ratio, or the relationship between your reactant and your product, which in this case, in every 2 moles, we would have to put the moles of NaN3 at the bottom. In every 2 moles of NaN3, you would have 3 moles of N2. So the moles of NaN3 gets cancelled, you are left with 3 moles of N2. So just plug this in on your calculator. You would have 75 times 1 divided by 65.02 times 3 divided by 2. You would get that you would have about a moles of 1.7994 moles of N2. And this moles of N2 is actually our N. So since we know that this is our N, we can now find the volume using ideal gas law. Volume of N2 using ideal gas law. So we know that the ideal gas law is PV is equals to nRT. Since we are looking for volume, we have to segregate the volume on one side and the rest of the other factors would be on the other side. So that is V is equals to nRT divided by pressure. So the volume of N2 is basically the moles of N2 that we have, which is 1.7994 moles of N2 multiplied by the R constant of 0.0821 moles atmosphere over mole Kelvin, and then multiplied by the temperature in terms of Kelvin that we just have converted earlier. That's 358.15 Kelvin. Everything divided by the pressure, which is in terms of atmosphere, that is 1.1513 atmosphere. So the atmosphere gets cancelled, the Kelvin gets cancelled, the mole gets cancelled. What you're left is liters, which is a units of volume. So plugging that everything on your calculator, you would get that your volume is actually equal to 45.96 liters. So that is basically how much liters of N2 we are going to get in our airbag, which will inflate it to protect us if ever we are have an accident. So that's how you would solve this problem. If there are any questions regarding this, please do not hesitate to message me. Okay, now let's go and move on to our other discussion, which is the Graham's law of diffusion and effusion. So let's first discuss what is the difference between effusion and diffusion. Well, basically, diffusion is the gradual mixing of your gases, creating an homogeneous mixture. So this diffusion happens usually even the absence of mechanical agitation, such as stirring. So for example, you have two gases, gas A and gas B, and you place those gas inside a container, and without even moving the container or without stirring the gases inside the container, because of basically the temperature and their kinetic energy, the gases will start to mix together until such a time that they create a homogeneous mixture. Homogeneous mixture just basically means that the whole combination of the two is thoroughly mixed, that if you take a sample from the top versus if you take a sample from the bottom, they're basically the same composition. So it's similar to this process right here, wherein the movement is also from the area of higher concentration to an area of lower concentration. So if you have noticed, for example, those perfumes that you put on your bathroom, so if you open those up, you would slowly start to smell the perfume inside your bathroom, right? And that is because the gas perfume, or the perfume into gaseous particles, will start to move from the container onto the surrounding area, wherein the gas particles will start to mix until such a time there is a homogeneous mixture everywhere. So the composition of the gaseous particles combination here would be the same as the gaseous combination particles here. That is what diffusion is. Another behavior of gas that is similar to diffusion is called an effusion. Effusion is basically when the gaseous particles move through a small, usually microscopic pinhole, and it is usually aided by pressure. So one example is if you have ever pumped a balloon and then you open the balloon a little bit, so uh, where you basically insert the air inside the balloon, and if you want to lessen the pressure of the balloon, you usually kind of like open it for a little bit, and because of the pressure of the gases inside the balloon, the particles or the gas particles usually escapes onto that hole. So just think of it that way. So for example, you have your gases here and you have your semi-permeable membrane. Usually because of the pressure, the gas particles will move past onto this barrier, right? So that is what we call an effusion. And we have a law in order for us to measure how much the rate of, or basically how fast a gas particles diffuse or effuse, and that is what we call the Graham's law. And it is stated that the phenomenon of effusion, it's basically the inverse proportion to, or the effusion, or the rate of effusion of gas, or how fast a gas effuses, is basically the inverse proportion of its square root to its molar mass. Sorry. What do we mean by that is basically this. So how fast a gas diffuses is equal to the square root of 1 over the molar mass of the gas. That is what we call the Graham's law of diffusion and effusion. Therefore, if we have two gases and we are looking basically which gas particles move a lot faster and how faster it moves, we can create an equation which is basically the ratio of the rate of effusion of those two gases, which is equivalent to the square root of the inverse ratio of their molar masses. So for gases A and B, we would have the rate of effusion of A divided by the rate of effusion of B is equals to the square root of the molar mass of B divided by the molar mass of A. So let's apply this principle onto a sample problem. So I've already solved this earlier. So for now, let's erase this so we can solve it. Oh, doesn't want to erase. It doesn't want to erase. Okay, well, okay, so how much faster does an hydrogen gas effuses than a neon gas? So basically, if we have our hydrogen gas and our neon gas, so our hydrogen gas usually stays in portions of 2, and our neons usually stays in that's why we have H2, and our neon would be Ne. So in order for us to solve this, what we want to do is first find our given, which in this situation, we don't have a numbers for our given, but we just discussed earlier that the rate of diffusion is related to their molar mass. Therefore, we have to find the molar mass of our hydrogen and neon. The molar mass of a single H is equivalent to 1.008 grams per mole. And that since we have H2, we just have to multiply that by 2. So the molar mass of our H2 is 2.016 grams per mole. The molar mass of Ne is basically equals to 20.18. You will find that in your table of elements, the number below the element, right? So that's 20 point grams per mole. So what's asking us is basically how fast hydrogen effuses compared to neon. That is the rate which we use R, rate of H2 divided by the rate of Ne. In order for us to solve this, we just have to use the formula for the rate, or the Gram's law, which is Ra is equals to Rb, or the rate of gas A divided by the rate of gas B is equals to the square root of the molar mass of B divided by the molar mass of A. So applying this formula, we can now solve for how fast hydrogen travels compared to neon. So RH2 divided by Rne is equals to the square root of the molar mass of Rne, which is 20.18 grams per mole, divided by the molar mass of RH2, which is 2.016 grams per mole. And that is equivalent to the square root of 10.009, and the square root of 10.009 is 3.16. 3.16 is basically how faster hydrogen gas effuses compared to neon. And that makes sense because for effusion and diffusion, lighter gases actually travels much faster. They effuses and they diffuses much faster. And since hydrogen, or our H2, is much lighter than our neon, it is about 3.16 times much faster than neon when it travels. So that's how you solve basically the rate of effusion or diffusion for a gas particle, or for a gas for a combination of two gases. So I hope it's clear. If you guys have any question, do not hesitate to message me. Thank you so much, guys, and may you guys have a great day.